We continued our discussion of wavelengths today with the Doppler effect. We've talked a lot about wavelengths already of stars and the information we can get from a star's wavelength, like composition, temperature, rotational speed. But here we're going to add in something. We're going to add in a star's motion using its wavelength. So what we know here is that a star spectrum can be used to determine if it's moving. And that motion we're going to notice is either going to be towards or away from us. And of course, when we say us, we mean the Earth. Right? We can tell if the motion of a star is either moving towards the Earth or away from Earth by looking at its wavelength. And this is known as the Doppler effect. Now, the Doppler effect was originally not used for stars, but it had another use in first, and that was noticing a change in sound of an object as the object moved towards and away from the observer. And this effect was then carried over from sound to light that we're seeing with stars. And we've all heard the Doppler effect before when something like a fire truck drives by, right? Or just a simple car. Okay, that object is emitting a sound, and so what we see on here are these sound waves. So this is a fire truck that is not in motion. It's stopped. And so we see a consistency of the sound waves going off of the fire truck in all directions, because that's what sound does. When I'm speaking, you can hear me whether you're in front of me, behind me, to the side. These sound waves are rippling out from the initial point, which is here, the fire truck. But as that truck moves past you, we notice that sound changes a little bit. We've all heard that sound walking down the road or at like a racetrack where we hear that kind of a sound. Okay, and that is the Doppler effect. So you've experienced this before. We just want to kind of understand why. Because that car is emitting one noise. If you were riding in that car, you wouldn't notice a change in sound. That sound would be consistent. But to the observer, as that car approaches and moves past you, that sound changes. And that change is the Doppler effect. So again, here's our fire truck emitting consistent sound waves. But what we notice is that as that car, or here the fire truck, starts to move, we see a shift in the sound waves. Okay? What we notice is that the sound waves from an object moving towards the observer are compressed. So as those sound waves, as that object is coming towards you, the sound waves are compressed. Right? And we can see here on the picture, now that the truck is in motion, those waves in front of the fire truck have now compressed together. They actually have a shorter wavelength than they did when the truck was just motionless. So as that object starts to move towards the observer, we see the wavelengths compress. And think about it, it's pushing the sound along with it. And as it pushes that sound forward, the waves are going to become a little bit closer together. And so what we see here is a higher pitch created due to the higher frequency of the wave as the waves are close together, giving us a higher note. So as that object is coming towards you, we tend to hear a higher pitch sound. But then as that object passes you, if you think of that car example again, we hear that kind of a sound, it will drop off as that object passes by you. And that again has to do with the wavelengths. Now, as the fire truck is moving past you, we see that the waves have been elongated. As the truck is moving in this direction, they're being compressed together over here. So I've got the closer wavelengths. We're back here, they're much further apart. Okay, giving me, as the object moves away, the sound waves become more stretched apart or further apart, causing the pitch to be lower or drop. Again, thinking about that sound of the car passing, right? It's going to drop down as the car moves past because the wavelength is getting big. So here's us, the fire truck has passed. We hear a lower pitch as the truck moves by. So let's get a little example going here. Here's our fire truck. I've got one sound wave for starters, and we see this arrow here showing us that the truck is moving in this direction. Because the truck is moving in this direction, we have to add the sound waves. So let's remember, as the object is moving forward, the waves in the front are going to be closer than the waves behind. So as we add in our circles, we want to extend them a little bit so the waves appear closer in the front and further in the back. And get yourself a total of 4 or so sound waves. It's okay if you get the little girl in there like I did. So because the truck is in motion and emitting sound, we know that as the truck moves forward in front of the object, I will see the waves. What type of wave will I have? They will be shorter waves. And over here, as the object is moving away from the observer, the girl here will experience longer waves. And in terms of frequency, because I've got a shorter wave, frequency again is how many waves per second. If the waves are shorter, they are happening more often, so the boy would experience a higher frequency note, where the girl over here, because of the longer waves, they happen less frequent, she would experience a lower frequency note. And so again, the reason why we hear that change in sound as an object moves past us is because of the change in wavelength. Right? As the object moves towards me, my wavelengths compress, giving me the higher note. As they move past, I now am hearing the sound waves differently because they've stretched out, become further apart as the object has moved past me. So how does this relate to stars? Okay, well, what we know is that light waves work in the same way as sound. They have the crest, they have the trough, they change their wavelength. So what we can see is when light waves, just like the sound waves, are compressed, that's going to tell me that the star is moving towards Earth. Just like we saw with the fire truck example. As it moves towards, the waves compress. Giving me shorter waves. Now how this looks a little bit different. We don't see the light waves emitted like a ripple as we do with the sound. We see them in terms of spectrum. So here is my original star spectrum. And what I notice here is that all these original lines are a little bit different than what we call the blue shift lines. Okay? Over time, this original star spectrum has slowly started to shift this direction, right? We can see here they've shifted ever so slightly from the original location. In which direction have they shifted to on the spectrum? They've shifted to the blue end. So we call that here a blue shift, saying over time the star's wavelengths have shifted ever so slightly this direction. The pattern is the same, but overall they've all moved in this direction, which is the direction of the blue end of the spectrum. And we know blue is also the shorter wavelength of the colors. So when I notice over time the spectrum line shifting, if I notice which direction they shift to, that will clue me in to how that star is moving relative to Earth. Again, comparing this original star spectrum to the changed, if I look at these, again, the pattern is the same, but they all have a slight shift this direction being towards the red end of the spectrum. We know red is the longer of the wavelengths. That clues me in that the star would be moving away from Earth. So light waves appear longer in this case of a redshift when stars are moving away from Earth, creating longer wavelengths, giving me the red shift. Pretty cool. So simply by looking at the spectrum, I can tell, is that star moving towards or away from Earth? Here's another example. Here's us, the observer. Here's the star. Here I see it moving away. So what do I notice about the wavelength here? This wavelength is much longer than this one, telling me this top example is going to be the red shift as the star is moving away, creating a longer wavelength. And here, this lower one with the shorter wavelength, that's got to be my blue shift, where the star would be moving towards Earth. Again, looking at the spectrum change over time. I can't just look at one spectrum and make this determination. I have to track it over time. Okay, so you have a little challenge there on the bottom. You've got the original spectrum at the top. Do what we did and kind of trace down and see if you can determine which direction these stars are moving based on their shift. Again, here, this top one, we can see from normal, they've shifted towards the left, which in this case is the red end of the spectrum. And here, we can see they've shifted this direction from normal, which is toward the blue end of the spectrum. So I will label this first example as a red shift, telling me that the wavelengths have gotten longer, the star is moving away from Earth. Here, with the blue shift, this star would be moving towards Earth, as blue is the shorter wavelength of the colors. Okay, finally, a couple challenge things or things to consider as we move on with our unit. The sun, we notice, has a continuous spectrum, but when we closely observe the solar spectrum, we notice that one side of the sun, so when we look at the sun like this side over here shows a red shift, but this side over here shows a blue shift. How is that possible for the star to be moving both away and towards the Earth at the same time? Okay, what we noticed here is the sun at rest, or when checked in the middle, has kind of no motion, but each end has a little bit of a shift to it. And so what we're seeing here is happening as the red shift is moving away and the blue shift is moving towards, what the Earth is actually doing is rotating. Okay, I'm sorry, not the Earth, the sun. The sun has a rotation to it, and we found out that stars have a rotation to them just like the Earth does. What else we've discovered with Doppler shift is the movement of galaxies. Okay, all galaxies out there in the atmosphere and the universe are showing a red shift. Okay, again, red shift is meaning that it's moving away as its waves get longer, so cluing us in that everything is expanding and moving a little bit further away from itself. As you wrap up this video, make sure you finish up your 2 summary questions. Check out some other Doppler links on the Moodle that we checked out in class, even a couple fun videos that I think you'll enjoy.